Okay, so we got several different measurements with different amounts of confidence depending on which meter stick we are using, despite the fact that every measurement was made with a device the same length. These two I can feel are a millimeter, maybe two different, but essentially, maybe that's just because that one was sagging, they're the same. They're both 1 meter. But when we started off with this, we had real trouble. I mean, we had some trouble making good estimates. But we had different levels of confidence too, where some were saying to the 10th, some were saying to the 100th. When we flipped this over and then saw it by 10 centimeter marks, we started getting more confident. Most people agreed at this. Got our next one that now measures to the 1/2 centimeter. More confidence. And finally to the millimeter, we're able to put it down to the 1,000th of a meter. We still don't necessarily agree 100%. And as I heard, there's still some difficulties with this. Are you lining it up the same way, everybody? With everyone. I heard complaints about, well, it's bending over this side, or other observations like, well, I wonder if we have it crooked. So all of those things can and do affect our measurements. And so what we're talking about today is how do we make measurements and report them with our different tools. And there are two different camps on this. One sort of a physics way, and the other is a chemistry way. Actually, we'll predominantly use the chemistry way for anything with calculation, so you guys will mostly be familiar with that. The physics way is probably a more precise method, but it's a lot harder to math with. So we're gonna mostly rely on the chemists for this, although today we are going to practice measurement the physics style. The things we have to keep in mind revolve around 3 terms. 2 that I'm sure you're familiar with. Another won't take a ton of description. We've got accuracy. We've got precision. Yeah. And then the new one that you might not have, but can come up pretty close with, is resolution. These will also, aside from resolution, will be in part of your first readings. So what we were dealing with first off was resolution. Resolution is the smallest increment a device can measure. So the distance between the 2 nearest marks. And I'm just going to put smallest increment up there. And we saw a big difference because the smallest increment on the first one was just 1 meter. That means that we're, in some ways, only allowed to measure to 1 meter. That's the physics way of doing things. When we get, and as we switched up to finally now the last one, that was down to the millimeter, so 1,000th the size of our first measurement. We'll come back to this topic for our work today. Accuracy says how close are we to the real value. This would depend on the resolution, because if we have to estimate much, we're not particularly good at that often. We can be reasonable, and sometimes we're a little farther out. But it also depends on the measurement device itself. If I had given you something like this in the first case and labeled this as a meter, we would have serious accuracy problems, even though you might use the tool correctly. So accuracy also plays into, is our measurement device worth anything at all? So that's a real concern. We usually trust our measurement devices. I gave this to you and you trusted that it was 1.0 meters. And it is, because I'm not trying to fool you. But that's potentially a problem, especially if we're measuring something that we don't have good knowledge of. We basically all know about how far a meter is. So you can say, yeah, this is probably right. Precision is related to how well can you repeat a measurement and get the same answer. So this is measurement repeatability. This could be from person to person. If they weren't lining it up with one edge in the same way, that would change our precision, even though the measurement device doesn't change at all and its accuracy doesn't change. If you put it at an angle and didn't realize it, that would as well. Most of the time, we just assume the accuracy of our measurement devices. It depends on the car. I've owned cars that the speedometer varies wildly. Like, not from drive to drive, but from car to car. So the one I drive right now is quite accurate. And I know that because I've used the mile markers on the road and I've timed it, and then you do the math. But I've had cars that are 7 miles per hour off when going 60 miles per hour. That's an accuracy issue. Now, the precision says every time it says 60, whatever speed I'm going, I am going the same speed. It might be wrong, that's an accuracy issue, but it's the same. The resolution is, how well do I know that? Is it marked every mile per hour? Is it marked every tenth? Is it marked only every 10 miles per hour? That helps me with confidence. And that's what we're going to talk about today. This is where our friend significant digits comes into play. Yeah, I heard some gasps of excitement, which is great, because we're going to get to practice that a lot. That's sort of the chemistry way to do things, but it is a far easier way to do them, mathematically speaking. I'm going to introduce the physics way today with measurements, because I think it might be the easier way to make measurements. And then later on we'll practice more with significant digits on how to propagate them and use them. So the physics way, that's not a good marker. Terrible. The physics way is to measure to the smallest increment on your tool. So that's step one. Whatever you're measuring, you measure to the resolution of the tool. Then you have some uncertainty. Oops, I'll put it on here. Uncertainty is how much could you be wrong based on that measurement? And that we use the notation plus or minus 1/2 of the resolution. So going back to our first measurements, we know through precise and accurate measurement that our tables were, what was it, 6.19. We'll take the average. 0.62. We'll call it 0.620. Just for argument. We can't measure that here. The best we could do on using this method is, well, I only know to the nearest meter. It is closer to 1 meter than it is to 2 meters, and it's closer to 1 meter than it is to 0. It was over half. So we would measure this as 1 meter plus or minus the resolution, half the resolution, which is 1 meter. So it would be written as plus or minus 0.5 meters. When we flip this over, now we know it by 10 centimeter sections, or 0.1 meter. So we could say 0.6 meters with an uncertainty of half of this, which is 5 centimeters, or 0.05 meters. And so on and so forth. Resolution of this is half a centimeter. So we could have said 0.6, and I'm just going to say that it's 0.62 meters, plus or minus half of this. Well, this is half a centimeter. Half of that is a quarter centimeter, 0.25 meters. And then finally we can flip it over, and maybe it's 0.619, because now we can measure to the millimeter, plus or minus 0.5 millimeters, or 0.0005 meters. This is actually a really good way to measure. But now let's say that we want to know the area of our table. And let's just call it a square table. We can square this number, 0.619 meters, easily. What do we do with that? That's why we're not using the physics way the whole way through class. It's great for measurement. It's really much more complicated for the math. So we will be reviewing and going over the significant digits and how to measure them. Just as an aside, the chemistry way to measure, if anyone remembers, would be to estimate to 1/10 of the resolution. So here, since the resolution is 1 meter, we could estimate to the nearest tenth of a meter. So 0.6, 0.7 would be fine. We would not still be allowed to go to 0.66, even if it looked like exactly 2/3. We just, by convention, we aren't allowed to do that. We aren't good enough judges. Here, we could estimate down to the tenth of this, 10 centimeters, so 1 centimeter. So now we could get 0.62 or 0.66 or whatever we wanted, and so forth. But for today's work, we're going to be practicing this by identifying what's the resolution, the smallest increment on each individual tool, and then the uncertainty we will just list as half of that, and we won't propagate it through multiplication or anything like that. Now I have another task for you. Use one of your devices there to measure the thickness of the black tabletop. Okay, what do we have for the thickness? Yep, whatever you like. It's fine.
In meters, 0.03.
0.31, you said?
Mm-hmm.
What's the uncertainty? Half a millimeter. So if we're in meters, how much would that be? Be half of this. It'd be a 5 there. So we point 0.0005. Anyone have something different?
Oh, we said, what was it? 2.97 meters.
Assuming you actually measured to the tenth of, to the millimeter, these two are the same thing.
Oh, I get it. Solid.
Okay? Now, we are running into the limits, and the chemistry way would be to estimate between millimeters to the nearest tenth of a millimeter. That's the problem with that method, because once we get past a certain resolution, we can't tell without more advanced tools. Something to hold the ruler there and something to maybe even a magnifier to see the tick marks. Mhm.
So some of that 3 centimeters exact, would you have to put like 3.0?
To preserve your confidence, yeah. This tells us how confident we are. So that is really an important digit there. There's a big difference between 3, which could be anywhere from 2.5 to 3.5, and 3.0, which is between 2.95 and 3.05. But we can improve our resolution and our confidence even more with a wonderful device called a vernier caliper. Okay, vernier, the caliper is just the shape and the type of tool. The vernier refers to the scale. And back in my day, before everything was digital and way easier to use, you might even find these, and we still have some in school, balances that use a dial that also have a vernier scale. It's a really, really nice way to do things in an analog fashion. But honestly, digital has replaced a lot of these things. So we use it because these are cheaper. You should all see a window that looks about like this. And as some of you have noted, this has 2 scales. We've got an inch scale along the top and a centimeter scale along the bottom. Of course, we will always use the metric here. And there, the way to read this, we actually get 1 additional decimal place of resolution. But it comes at the cost of being a little trickier to read. So the first part of this is we use this bottom, and this is our 0 marker. It will tell us the 1s digit and the 10ths digit based on where it is, and we'll always round down to the nearest. So this one is basically, it's after 3, and it looks like it points very close to the 1, the first digit after it. That would mean our measurement should be 3.1 centimeters, and now we're going to add another digit afterwards. So the way we do that is one of these lines is going to line up very, very well with a line above it. We actually don't care which line above it, it does line up with. Our final digit, which will be in the hundredths of centimeters, comes from which line down here lines up. Let's see if I can write on this. Here is my 0 line, my 1 line, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So my first part, this, tells me it's probably 3.1 centimeters. Go through and see which of your lines under here lines up best with the line above it. That will be our final digit based on these numbers across. If it's this first big one, then our last digit is 0. My measurement up here is 0 because this line is really close to the center. This one is just a little bit left of center, and none of the rest of them line up well either. The closer you get to the true digit, the better they will line up, so you have to be pretty careful. Also note that the 10 lines up almost perfectly over there. So the 2 ways to read this are 3.0, 10, so that gives me the 3.10. Or 3.1, and then it's the 0 here. We know it's not up to 3.2 because our 0 line would have to be closer to this. We're going to try a couple different things, like try a book or something. Yeah, so you measure something, I don't even care what it is, come up with your agreed upon measurement of whatever you just measured. Call me over and I will verify that you read it correctly.